Hey, how's it going, guys? Back again. So, we are still on this daunting process of doing some, to me, it's daunting, but some data analysis for HVAC system operations in a retro commission style with this Vibe Code App 19, which is a Streamlit application. Um, Check the prior videos for a little bit more deeper dive on what Streamlit is. This is it. This is just it's a data science application for how to spin up web dashboards. It works really well, and the data science community likes it. And we can also kind of harness this for doing fault detection purposes too. So a lot of data science or analysts use this framework to quickly spin up reports and dashboards, and you don't have to be a full-blown software engineer to do all of the front end HTML and JavaScript and everything like that. So there's a couple different dashboarding uh, frameworks out there, and I'm just using Streamlit just to vibe code our fault detection application. And then also where this is in the vibe code app 19. Um, we did yesterday just show how to bootstrap it through Docker. Pretty easy if you have Docker on Linux or PowerShell or Mac. This will pull down the latest container where it's published on the GitHub container repository under the BACnet Stacks Playground Vibecode App 19. Then how to run the application, which is this Streamlit application, and then we just dial into it on port 8502. So, which is right here. So, feel free to, if you want to try this out, just ask some questions on Discord. Ask me directly. I'm also freelancing on an hourly rate. So, if you want some more assistance, I'm definitely available. If you have buildings to look at, I'm definitely very available as well. Um, okay, so where were we going next with this? I'm just started to make kind of like a generic report, but the latest and greatest, we kind of went over this the last couple days, like this overview, rule validation, and everything like that. And then there's also a report, just a very generic report template that you can download as well. So it's just right here, this big button, download generic report template, which is this. I'll just go over what I have so far as well. This is going like way slower than what I was originally anticipating, but it's a lot of I was hoping to do some of this with like fault detection with AI tuning, but it's just so not there yet. It's like the stuff is very manually. I think you could do some like very high level stuff, but then it really takes like a person kind of diving in really deep and yeah, I just have it could be there someday that I think like someone could write like the skills markdown files or whatever, like what the AI agent could use to do assist with HVAC fault detection. But someday it'll be there. Just maybe not right now. So I have this defined already in my Streamlit application, and somehow it lost the settings. But this is like where we talked about this yesterday, where you define the building's occupancy schedule, um, which differs a little bit than a building automation schedule because that's constantly changing. The maintenance staff is constantly, more than likely, they are constantly revising the building automation schedule to handle some kind of a temperature control complaint in the building, which this building has some of that going on too. Like I can tell that um, the equipment runs longer during some conditions outside and then shorter during others, and that's common that you run HVAC equipment longer if it's really hot, and shorter if it's very mild outside. very mild outside, just like a residential system. You don't even need heating or cooling at all. So that's when we would be running in a bare minimum. So I just have to get back to this open on Saturdays at 7 a.m. And then we're also building closes at 2 o'clock in the afternoon and then closed on Saturdays. I think I might have to make some kind of a feature that you set the schedule once and then it locks it in. And then degrees Fahrenheit, this is like the range that the owner said that they need to maintain 72 degrees, and typically there'd be like a 4-degree dead band, 2 degrees up and down. But kind of like a generalized comfort range can be 70 to 75. And then this is where we're ranking zones, bare minimum run hours per week. So we covered this the last couple of days. Won't go over that anymore, but just some of these binning, mechanical cooling run times, and then kind of tracking weekly equipment run times for both of these air handling units with a bare minimum run time. This is like a dashed, I just like zoom in like completely. There's like a dashed brown line here, and that is the bare minimum run hours per week, 62 hours of what we defined in our weekly schedule picker. And then we're also plotting average outside air temperature too, so we can kind of gauge that like they're running equipment longer or shorter. Okay, so we covered that. And then I do have started this. This is just a very generic report. So my background is not report writing. I am not good at report writing. So this is just some very generic, I'm sure people have much better reports, report templates, and everything like that. But if you don't have anything like me, then, this will get you off the ground. And then just make it into whatever is more professional and everything like that. So I'm just going to start a report for this building in very kind of traditional retro commissioning styles. Typically, what I'm missing is like an appendice, and then also like beginning of report. There's just like a summary, like go to page this, go to page this, auto link to different pages. Where if you want to go to the air handling unit, go to page 11, VAV page 20. Like those summary tables with the page number links. I don't have that at the moment, so kind of bear with me. It's kind of not half-assed, but it's good enough for like a concept idea. And then this stuff will be improved. So the next building will be the next iteration of this application, and then bugs, all that kind of stuff too. One thing that I did fix, and I'll show this to you, is so if I go into fault detection plots, there's a bug in the sliders over here where I used Fable to kind of comb through the fault equations. Reference the prior videos too of kind of a deeper dive into where to find the fault equations. I'm trying not to be super redundant on every video, but so there's 58 fault equations now, and then they're all on the Open-FDD repo. And then it was in not the SQL version, but the pandas version. And then I'll probably have to keep on updating that because I'm making things a little bit better as we go. So the expression rule cookbook will get updated continuously, which I'll probably have to do another update on that today. Okay, so like sensor range faults, flat lines, sensor rate of change. This is something new, like sensor rate of change. I'm just actually going to start another round of Git issues. So this one from yesterday is fixed. Close all that. So close the Git issue. Let's start a new one. So this is Liberty Building 100 work on 14th of July already. Sensor range faults is hard to what sensors are in fault. It is itemized. Okay, so this will be anyone else out there to create a GitHub account and then try this out. And then like where you find problems, if we Git issue this stuff, we can fix it, make it better. That's a community-based project, is to continuously make things better, and all open source. Okay, so I do have a bunch of this. Sensor out of range, sensor flatlined, sensors rate of change, allowable rates of change for traditional HVAC system faults or types of sensors. So some of this might just need like a little bit of work, but I did a little bit of research for the type of sensors in HVAC systems, like zone temps, discharge temps, mixing air temps, water measurement, temperature sensors, humidity. There could be like leaving air temperature after a DX cooling coil or a gas burner or a chiller, so different sensors have rates of change of what is be expected or allowable. So that's all getting baked in here, except I need to beef up like how I'm reporting on this as well. PID hunting, so anything that has a control output. So this would be anything on an analog output of like a 0 to 10 volt signal or 0 to 100% signal for a damper or a valve, a reheat valve, a pump speed, something with a PID. That's something's modulating. So this will be acceptable changes per hour in that range. We should cover a deeper dive into this too. Yeah, so there's a certain cycles per hour for this PID hunting. So let's see, we should probably at some point in time even look at the Python code that crunches those numbers. Pandas is perfect for that kind of stuff. Okay, so this is like some of these are skipped, so that means it didn't apply to the data model. So this air handling unit was just, if you remember the pictures from yesterday, it was just a variable volume air handling unit, cooling coil, and it's a mixing air unit. So just a kind of a traditional supply return fan, variable volume, duct-sided pressure control with one cooling coil, no heating coil, an economizer. So so we do a little bit of data modeling and something kind of haystack like. So we use haystack naming conventions, and then we map the CSV column name, the raw point name, to the haystack name, and that's something that I used AI to do all of that mapping for me. And then I iterate over the faults that would apply to the air handling unit. So this is what it means by skipping. It doesn't apply to the data model, but I do see like this is what I was trying to demonstrate yesterday is I think it was this one yesterday. So like this is like a supply air temp and mixing air temp mismatch in full economizer. So this would mean the economizer damper is wide open, the mixing air damper mapped in through haystack. Chilled water valve is open 10%. And then there is a supplier temp minus mixer temp, there is some kind of, this is just some goofy, not goofy, but it's just like a guideline 36 way of defining the deviation of the temperature sensors, allowable deviation to a tolerance. And we recut 26% of the time that this is in fault. Oh yeah, so this is our, this also shows mapped points through haystacks tags. So this is our haystack tag right here, and then this is the raw column name. So you'll be able to see this through every fault detection rule. Okay, so let's go look at this. Fault condition 8, guideline 36, fault condition 8. Go to the drop down here. Fault condition 8. And then you'll see like the little triathlon guy. And this Streamlit application means crunching some numbers in the back end. So I just wanted to demo like where this the little tuning parameters are fixed. Okay, so like we're measuring some, see these little faults down on this row, and then this is the percent column. So so there's 3 plots. This is degrees temperature in Fahrenheit. Anyone that wants to play around with this, if you're on the other side of the globe, please test this out in metric. Just hit the metric button. That needs a validation for any the rest of the world that's in metric. Why the United States is imperial units still, I have no idea, but please try the metric units. Unfortunately, imperial units is the only thing that my brain is used to viewing. So if I look at metric data, it doesn't make sense to me when I see, metric data. I'm sure you say the same thing on imperial units. Okay, so this is temperature. This is percentage up here. All data model driven. So this is mixing air temp, discharge air temp, outside air damper, cooling valve, and confirmed fault. So let's just zoom in on a confirmed fault. I mean, there's not much of a deviation here, a little bit. So I will do it even, well, let's just take a note. I'm just going to screenshot this day. This is a day in March, where in theory would be perfect. Free cooling. So we measure, yeah, this is a great free cooling day, that the outside, let's see, discharge air temperature and the mixed air temperature. This should be, if the air handling unit's in 100% outside air mode, the outside air, mixing air, and leaving air temperature should all be pretty close. And there's just a little bit of a bump on the leaving air temperature. You account for fan heat, which is usually a degree or 2 bump from the fan motor. Okay, so we're getting some faults here. So just like this yellow line is showing that the outside air damper is 100% open. There's also some really funny things in this data that this 100%, I'm starting to wonder if this means 100% closed, because there's just some things that just don't make sense. I'll show you later. I have this documented. But okay, so like let's play around with tuning this fault rule, fault condition 8. So let's just bump up our tolerances. Okay, so I bumped up tolerances there. Where'd it go? there's like a delay parameter, so I can even bump that up too. This is for a proof of concept that this changes. Bumped up our tolerance from 1.5 to 3 degrees Fahrenheit, and then rerun rules. Crunching some numbers when it gets kind of gray. Little triathlon guy goes. And let's go check this fault again. The only thing that is kind of annoying that I could probably fix in the future is it's not very easy to tune a rule and then see it instantly reflect in the... Okay, so this was March 23rd. That would have been around here. So I just made that day completely go away. March 23rd, there is not a confirmed fault there anymore because these tolerances have been changed. So that's just an example of like how the fault rules can be tuned. Yeah, I have to ask that owner because something doesn't sit right. That this outside air damper is always 100%. Because you can see in the data like that when the fan goes to zero static pressure, that this never changes. It's either that this is, I have a hunch that this is 100% closed all the time, and something's not right. It's either 100% closed all the time, and there's just, it just never opens. They don't economize. They don't ventilate the building at all. Yeah, it just makes no sense because like when you would shut the unit down, that you'd always close the dampers. So you would expect to see fan status and damper go to 0% all the time. But yeah, there's something off. Okay, so we can see that these air handling units, so these are tracking each other. Like, and like the air handling unit would be almost in 100% free cooling. There's about 2 to 4 degree between the discharge temp and the mix temp, 2-3 degrees. So the unit has to be in 100% outside air mode here. There's a few things that look really odd. So like I might just go into RCX plots. So this is just like a very generic way of plotting data. Let's just go back into air handling units. So, okay, so we can look at supplier temp, air handling unit supplier temp. That is not something we need to look at. Supplier temp versus, I gotta fix that. All discharge air temps. Back into May. Hmm. Looks a little bit strange. Okay, so like we wanted to see, let's look at all outside air dampers. So this should be both air handling unit outside air dampers, filtered from when fan is on, and they both just sit 100%. So yeah, there's just something very unusual about that. It would be nice to get. It's just odd. So summary statistics, they're even like the mean standard deviation is, this it's very unusual. So like stuff like this screws up the fault algorithms too, because the fault algorithms expect to see the percent of the damper or output change. So okay, so where were we? So like I started a very generic report. So this is what I'm going off of, like reduce unnecessary mechanical cooling when outside air conditions suitable for economizer operation, minimize equipment runtime once occupied zone temperature requirements have been satisfied. So this would be airside systems. Calibrate or replace the outside air temperature sensors. Consider using validated web weather data in the Niagara building automation as a primary outside air temperature source with a automatic fallback to local outside air sensors whenever the web data becomes unavailable or stale. And then this is something where we could also put consider outdoor point as economizer logic termination. Implement supplier temperature and duct static resets for air handling units. Okay, so I have this too for like troubleshooting worst performing VAV box zones. And then I might have to go over this again, like key conclusions, economizer and cooling control. So this is where I pulled this right from the start that occupied zone temperature range is 70 to 75, Monday through Friday, 7 a.m. to 6, and Saturday, 7 a.m. to 2, closed on Sundays. And then this is like these same plots that we've gone over quite a few times already. Just equipment run hours. And we can also, we also have analytics for elapsed um, run hours of the equipment um, against the bare minimum. So like any of like this, these run hours above the bare minimum, there is a totalized value for that we could, it's a fault basically. And then we can actually, I'm not doing this right at the moment, but we can actually be doing energy equations in here too. So like um, very kind of stick your, wet your finger, put it up to the wind, and then kind of rough guess of like, if we know, I don't even know the size of these fans and horsepower, and then like the chiller and everything like that. And like we could, like we can estimate electrical power and then turn that into a kilowatt hour calculation. Then these can be submitted to the utility local utility rebate program for incentives. So if there any of these recommendations, if we put a an energy calculation to it, the owner can get a check cut directly to them for implementing these algorithms. I've seen it too, where if there's like a really good utility rebate program representative for your area, that they will assist you even with doing some of these calculations, as long as you can provide them the data that I've recorded that this equipment runs on average 100 hours longer, um, that kind of thing. And then they can even assist you in getting a check, writing a check to the owner. Maybe it could be $500 or something like that. um okay, so we've talked about this several times. Reducing the chiller run hours during these hours. Okay, so this is I actually started porting this over to a different section of the report. So okay, so this is just my summary, just my little data model here, that the Streamlit application with the AI assistance, we've modeled 2 air handling units, 1 boiler, 2 chillers, and 43 VAV boxes. so this is air handling unit 1. So besides these other things, I've also found that this air handling unit has a low duct static pressure. At certain times, I still can't figure this one out either, that at certain times, so for starters, fall condition FC1, that's guideline 36, fall condition for variable volume air handling unit does not meet duct static pressure at full fan speed. And I can calculate 71 hours, 71 fault hours on this data set that's, I think it was 700 hours long, that during that at times the air handling unit appears to run longer than the air handling unit does not meet duct static pressure during this time frame either. So this is kind of a common thing that I see is that, so this is this is just a 1 day, April 23rd, for example. Air handling unit starts around this time. So it goes from 0 to about 75% speed. This orange line here is the duct static pressure. And we saw in the graphic that the duct static pressure set point is 1.65. So that immediately goes up to duct static pressure. And the fan even backs down a little bit. So that looks normal, no pid hunting. And then it maintains duct static pressure just fine until about this time of hour 1800. Something odd happens. I think what's happening is that the chiller is on its own fixed building automation schedule, and the chiller stops. And then there must be programming that keeps on making this air handling unit run longer than the chiller. So the chiller stops. I have a feeling that so does all of the lovely chilled water for the air handling unit. And then what happens is that the orange line here is like the duct static pressure appears to drop. And then the fan goes up to 100%. And then that's when we flag this as a fault. So this particular day we have about 6 hours of fault. It's not every day. It's not a very repeatable pattern in the data set, but it happens on very unusual times. Just my own hunch is that the chiller is on its own schedule. Chiller shuts down, and then there's some additional logic in supervisory level layer that keeps this air handling unit running, and there's no interconnection of the chiller and the air handling unit. So the air handling unit keeps going, and then all my cooling has gone away, and then all of the VAVs are asking for cooling, but they can't get cooling. So air dampers open up, duct pressure goes down, and pretty soon there's you're blowing around a lot of air in the building for hours at a time, wasting a lot of energy. So I just have a recommendation to document and revise air handling unit runtime logic. I don't have the time to do it, but this is also something that there could be like a very generic energy penalty estimation for this to get that utility rebate check. Another one I have too that we talked about earlier is that the outside air temperature and so this is Econ2, this chart called Econ2. So in here, if we would go to back to fault detection plots, we go down to Econ2, economizing when outdoor is unfavorable. And I think there's something unusual going on with this building. That this outside air damper is either 100% closed all the time or 100% open. I think it's just closed. And then I think that I have a hunch that this building is the economizer dampers may not economize at all, and then that's why they need the chiller so much. Um, that's why they need the chiller operating at these hours, is that these dampers don't work at all. This is my hunch, and then that they need the chiller to run, even when it's below 55 degrees outside. If that's the case, uh, there could be there could be a reason to get the economizer dampers fully functional. Like in this, I assume that the building was designed with fully functional economizers. Seems like any building built after 1980, or something like that in the U.S., like by energy code requirements, they have to have them. So it would be very unusual that it wasn't designed with economizers. But it could be like a really easy preventative maintenance too. That if the sometimes like mechanical contractors, like when they sell a service agreement, it's usually like a quarterly PM. So there'd be like, oh, heating season preventative maintenance, cooling season preventative maintenance, and then something in between is perfect for validating fully functional economizer dampers. Building automation service technicians, this is like a perfect one too. It's just uh, shutting the air handling completely down, and then fully visualizing that the dampers actually close and then that they open. And yeah, and if that we need that like visualization that these dampers fully close and they fully open and there's good seals. A lot of the time some of this equipment is so old that there's rubber seals, gaskets on the blades of the economizers, and sometimes those are gone. Um, really old air handling units, I've seen in the mixing chamber a pile of rubber gaskets that have just fallen off the blades, and then it's pretty soon it's just economizer blades. There's no seals anymore. So like what also happens is there too is that they can get, even with it fully closed, without gaskets there, that they can still get enough ventilation air with them fully shut because they leak so much. But it also causes a lot of problems if it's really cold, or if it's really hot, humid air, and you're ventilating the building too much. You're having to condition that really cold or humid air. Then it's an energy penalty again, and then it could. I feel like involves like a deeper dive that someone could validate that first. Service technician go on site, validate those dampers, actuate good seals. Um, if they do, we should let's get back to that screenshot. Building 100. If these dampers do, and the seals are not broken, so they would go and they validate these in the field, then we should be putting this discharge air set point back to 55 for peak cooling season, and then floating it upwards in the uh, shoulder season, or doing some kind of a calculation for duct static pressure reset, and then also temperature reset too. Um, I'm not measuring any leaking cooling valves. Uh, I don't see anything wrong in the data on that, but there's something really off here as well. I also have a hunch too that this right here um, used to be the box where the minimum outside air damper positions were for the air handling unit, but it's gone. They've just removed it, deleted it. Um, Over time, it's just might be easier to operate the building that way. And then if they don't have any indoor air quality concerns, or these dampers are so old that they leak a lot of air, you might not even need it anymore. But as long as you're still, I just don't see anything in the data that these economizers are that there's any free cooling going to the building at all, and that there's any uh, minimum position for ventilation air requirements for the building. So I also would be really curious to know if they have building pressure control problems. If there's toilet exhaust systems in the building, that typically the air handling unit, by design, provides the makeup air for those exhaust systems, or else it comes in unwanted places through cracks in the building or through the doorways, whatever. The most ideal thing you'd want is to be makeuping the air handling unit should be making up that air for exhaust systems and then conditioning it as well through a filter and then through some sort of a cooling coil if it's humid outside like it is now. Okay, so where else am I going with that? So there's something really off in here. But that's in my this is the meat and potatoes in my summary so far. Um, something really something really requires a deeper dive in here. And I'd love to take a deeper dive into this more. So let's just go back into. So we do have some of these fault equations. We did look at this before. Is the local outside air temperature sensors versus data from the web. So the two, jumping around here a little bit. So the two zip files. The next building I do and demonstrate, I can demo a little bit more on the AI required process on it provides a mapping in a JSON file for web weather and just CSV file data. So if we just look at, of course, now and here's another problem, is that okay, so I have a messed up chart. We needed to be plotting web weather against web weather outside air temp versus local on the same chart. And then our fault is actually when these are deviating from each other. So this percentage chart here is, we don't need that at all. So like here, I'll just kind of line it up on this axis. Web weather is at 51 degrees, and then local is 38. They do track each other. 71 on the web weather and 71 right here. So they do, maybe this could just be flatline data right here too. I have a feeling that this is just flatlined missing data. They do track each other. My earlier hunch of them requiring this was because I thought it was because there was a deviation between the web weather and the local outside air temp sensors, but I'm beginning to think that they do this because there's a problem with the air handling economizing dampers. That's my own hunch. So let's just go back into. I still have to do air handling unit 2. Let's go back into fault detection plots. Okay, so let's write this down too. Okay, so web weather versus outside air temp local needs to be plotted together with the percentage column. We should only be plotting two lines of local versus web and Boolean that needs to get cleaned up. Okay, so where were we? So let's get back into our little app here. So I wanted to go back into, there's something off in here too. I think this might just be a label issue. Okay, so like RCX plot fix label of HU versus dry bulb scatter plot, not wet bulb. Back to this, it shouldn't be wet bulb. You only need to look at wet bulb if you're looking at some kind of a cooling tower or evaporative cooling. I think this is a mismatch in the label, but this is what we're trying to depict here. So let's look at air handling unit 1. Or this is air handling unit 2. But yeah, there's some anomaly in the data right here. Let's just draw get our chart a little better. Okay, so they do not have a very good discharge air reset in this building. Seems like it's consistently. So this is the discharge air leaving temp. It's around, as soon as you get to above 50 degrees outside, I just kind of see in the data that it drops to about a 48 degree discharge air temp, which does kind of reflect this discharge air. Those is air handling unit 1. Discharge air set point of 50, which seems a little bit on the cold side to me. And then as soon as you get below 50 degrees outside air temp, the leaving air temp kind of floats around a little bit. There might be some kind of like a algorithm on the building automation system that's does something right around here. And looks something similar to air handling unit 1, which does have about 55 degree. Could look some data down here too. So something right about here. They do something kind of funny. I mean, it's not a bad thing to lock it in at 55 degrees, especially in this building's location. Very humid, and 55 degrees Fahrenheit is a very common design cooling parameter used for air handling units. Except usually you don't need 55 degrees until you're like, way up here when it's kind of warm outside. I don't know. Point being is like there's not a really good. There's not a lot of data for like when it's colder outside, but I think there is some kind of an odd discharge air temperature reset going on. If there is anything, I think it's just one latch, kind of like if outside air temperature is greater than 50s, it just locks it in. And like another thing I want to do is, so we looked at outside air dampers, and let's look at here. So this is duct static pressure. I was curious to just look at it in box platform, because we did actually look at it in a time series chart on the fall condition 1 fault detection plot. So like I kind of like duct static pressure. So that is this sensor right here. So like what the fan does is this is a variable volume fan on a VFD drive. I have no idea how big it is, how much horsepower or the volume that is designed to push, but like the control PID behind the scenes would be output would be fan speed and maintaining the set point of 1.56 inches, which there's no hunting or anything like that, but there's no reset of it either. So like they're just maintaining a constant 1.65 inches water column, where there could be some optimization in resetting the duct static pressure. Hopefully that makes sense. So like this sensor is typically a needle in the haystack. It's installed like 2/3 the way down the duct system. Who knows where it is most of the time. And then this fan is pressurizes the duct system for static pressure. It's like blowing up a balloon, where this fan is actually operates like a kid blowing up a balloon. So it's pushing pressure up, trying to push the ductwork apart. So that's static pressure. 2/3 the way down the ductwork is where the control sensor lives. If we were doing a guideline 36, we would be resetting the duct static pressure based on demand, which would come from zone level input from VAV boxes and resetting the leaving air temperature set point. Yeah, so they're definitely not doing that. And I feel like there's some broken band-aid in the building that needs to a further deeper dive before we could start doing duct static pressure and temperature resets. But you'd be able to see that in a box plot. Here's some anomalies here in the data that at one point in time the sensor read 7 inches, but that could be something odd. But if you would look at the box plot, you can also tell like this air handling would have problems too. So this is 50% of the time it nails it right at 1.5 inches. So this is quartiles. So basically these are little outliers right here, and then 50% of the data is in between here and here. So we can see that here. Fan on statistics. So 50% of the data is in between 1.5 and 1.6 inches of duct static, which is pretty good. That is like between here and here. And there's a little bit of data where it is, no, I'm sorry, it's air handling unit 1, it's 1.3. Yeah, 1.3 to 1.3 to 1.6 quartiles here. That is this right here. From this bar to this bar. And standard deviation is 0.13 inches water column, where this other air handling unit 2 performs a little bit better. Let's reset our access. Air handling unit 2 does much better. Like it nails it. That's why I think air handling unit 1 has all of the duct static pressure problems. Fault condition 1 equation, guideline 36 is flagging that, and then we see that in here as well. But yeah, air handling unit 1, this system has some goofy things going on where it causes the air handling unit duct static pressure control to like if there's components downstream that aren't working right, it'll mess up upstream components like the fan, control. Something is going on. A little bit deeper dive in this building is required, in my opinion. Okay, so let's just I think we're gonna have to call it a day here pretty soon. I just wanted to show you they also have a future column for metering that's I haven't gotten into it here, but maybe I'll demo the next go around. I have an old data set for a school district that had a mechanical retrofit. Um, just looking at electrical meter, maybe we'll demo that one on the next one without any HVAC, and then we can look at the data model a little bit more to kind of show you how that works. Um, okay, so like if we go, we can also drill into individual VAV boxes. I just haven't had time. Sorry, like, do we have that on this data set? Okay, so zones. Okay, so this is the last thing I think I want to just cover. Behind the scenes, the Python pandas library is doing this z-score for anomaly detection, and I think this is working pretty good just by what it has by default. So it'll flag these guys as outliers. Um, okay, so this is filtered for when the fan systems are running. Something I also have to get uh, feeds relationship from the client on which air handling units are feeding which VAV box, and then we could even do like a further dive into VAV box level components. It would be really interesting if we could really diagnose what's causing some of these problems in the mechanical system. So this data is filtered for when the building is occupied, and there is something is going on that's all squirrely. Like look at this VAV box that continuously reads 100 degrees. Wow, VAV 22, 100 and something's going on with that one. And then if you see the ones with little stars, these are the ones that are outliers too, flagged by this z-score thing. So if we look at this, this is just some statistics for worst performing VAVs. And it's just documented by percentage of time when the air handling unit, when the building's occupied outside of that original 70 to 75 degree comfort band. So this VAV 7, 100% of the time is outside of that. VAV FC1, 88% of the time. VAV 3, 81. And then a couple of these aren't that bad. So you need to get down here, 1% of the time. So this is just ranked for, and I would probably, if we knew like which air handling unit these guys belong to, so I could even download this. Let's download this as a worst performing. Open this in VS Code. So this should also be something we could open. Maybe we should just do this right in Sheets. I actually don't have. Actually, sorry guys. I think I would actually just have to go to. Um, I'm sure I don't have Microsoft Excel, but I think you get the point. Is like, I can send this to the client, and then this is you could just open this in Excel. Um, And I would have them like look into this, these worst performing VAV boxes. I think there could also be like a better chart here. Um, Kind of wondering like what kind of a chart could be. Maybe we'll do this too. Worst performing VAV box, better chart. Say pie chart. VAV percent time outside of comfort band. I think I might just end it at this one, guys. Trying to wrap this video up, but like the so I'll probably just if I could tell the client like maybe these I wouldn't be surprised if like these zones are probably something to do with the air handling unit 1 system. Um that looks kind of odd. So I'll send that to the client. And then let me just like I don't think we covered like um actually I'm sorry, this like fault detection plots. Just want to go back through this app is a little bit slow. Just look at air handling unit 2. I know that air handling unit 1 seemed to be the one with the majority of the issues. So this is like where you could drop down and then look at the different kind of plots you'd want. This is down here, left hand side, how you tune faults. Let's just kind of look at some of this so you can kind of see. So, triathlon guys up there. Still crunching some numbers. I think like this app will get like better and better too. So this guy does have even air handling. Let's see if okay, we're still in air handling unit 2. Still have a little bit some of these issues with mixed air temperature sensor is not in line with mixed air temp is below the outside air and return air temp. Some anomalies with the mixing air temp sensor. Couple faults on the duct static pressure, maintaining duct static pressure, but I don't think it's nearly as bad as the air handling unit 1. I think I did record 59 fault hours. Let's look at this one too. One, another thing that we were kind of trying to talk about is this building covered the shoulder season really well. Um, and so like when it covers a shoulder season, that's when we can really look at the um, economizer performance is kind of like the what we should really be diving into for shoulder season. If we were doing peak cooling season, then we would be looking purely at chiller plants, making sure we are not economizing when we um, should be, that type of thing. Wow, look at this. This is actually duct static pressure does reach 7 inches of duct static. Okay, so there is some like really odd things going on here too. Wow. 7 inches of duct static, and the so like okay, so what day? 23rd. Um, oh boy. So this fault does not measure that. We should have like a fault high static pressure too running. So something is very wrong here. Very wrong. Um, so like a fan is stuck in hand. Normal control signal, and then it's like the air handling unit go does not stop, but all of the dampers in the system do, and it's measuring 7 inches of static pressure all night long. Wow. Little fault here, right here, but it's not flaking this. Okay. We should have a. What is this? Duct static high fault. So let's just look at this one. So this is duct static high. Let's see how many fault hours this is. So if this is the other air handling unit, but I think the graphic is the same. So this duct static pressure is reading really high levels. Like this fan is running in a manual fashion um, when it should be off. Okay, something's wrong with this fault rule. It's not working right. Um, Look at that. There's this. So I'll just zoom in on a day like right here, and it looks to me that all night long, this air handling unit is running in hand, and then it takes off in the morning. Hopefully, you guys are seeing this too. But like, for one thing, fog, duct static, pressure, this fault. I think I haven't. I know why it's this fault should ignore fan status and be running regardless if fan status is. I have a feeling this fault is not picking up this because there's like the fan status might be functioning, but the so what I mean by that is this is the fan command, and then usually there's status right here is linked to the little widget in the graphic if you could see the animation. So this is probably working right for some reason, and the fan by controls are going to 0, but this sensor is going through the roof into. I'm just guessing is that VAV boxes downstream are shutting down for the day. They're going home. So is the air handling unit, but something in this fan is like keeping, 7 inches of duct static is not something that you would really want. Okay, so I'm going to download this and kind of probably call it a day here, guys. So I'm just going to send them this reducing chiller run hours, which I think is directly related to my own hunch here that the economizer dampers are locked out, broken, abandoned. Getting those economizer dampers working again. And then all these issues with the duct static pressure, and then these worst performing VAV boxes. It would be really interesting just to know a little bit more about that. And like my opinion is like once that once these items are fixed, then we could even go into Niagara Vibe Code Addict. So then we could get into Trim Respond. But I think this building is just like might need some a little bit more things to be fixed in it. And then once these are fixed, then and we can validate it again with fault detection charts. Then I think we could get into optimization. I do have on the Niagara Vibe Code Attic free pre-built wire sheets for air handling unit duct static pressure and temperature, and these have been validated. Like I implemented these on a previous employment on about 60 air handling units for Guideline 36. And then I think the other thing worth is I do have a Niagara widget for Open Weather Map API. So these are the two things that I want to recommend prior, both free. They're cost nothing. In the local building automation technician can kind of throw it on. And yeah, a few concerning things in this building that just don't make sense. So hopefully you guys are liking this. This is a long video. Sorry for that. But and I'm just throwing it out there. Is anyone else that wants to have some sort of analysis? I'm kind of throwing this out there. Is look me up. Look me up on Discord. I like this kind of stuff. It's very time consuming, so I'm kind of trying to like freelance myself, and I'm just offering like one free analysis deep dive into if you have some like really if you have good data, you need to have good data, a place where I can download CSVs really easily, send to me the CSV files, or if you have an IoT provider that is your data provider, they can send me the data or they can show me how to download it from their API, and then I can do this free analysis and we can look at it together. So hope you guys are liking this, and I will catch you on the next go around.